Well, it's a particular pleasure to introduce this afternoon's speaker, Matthias Treuer, who's a longtime affiliate and now a trustee of the Center. He will tell us about quantum computing, one of the most exciting developments taking place in physics and indeed in all of science, and one that will have a lasting impact on all our lives. Just to get some idea of the scale, think of the iPhone in the mid-2000s before it came out, and how that has changed our lives. Well, this will be much, much bigger. Yeah. Well, despite popular imagery, there are really three different approaches physicists take to study the world and put together a picture of how things work. First, and quite critical, is the actual doing of experiment, or in astronomy, doing observations, simply getting the facts. The second is thinking about physics, the sort of Einstein image, where with only pen and paper one slowly begins to understand the experiment and even make important new predictions. If you look back in the late 16th century, Tycho Brahe, sitting in a little island between Denmark and Sweden, did the first accurate measurements of the positions of the stars. Within 10 and 20 years later, his postdoc, Johannes Kepler, made sense of all the data, really setting the stage for Newton's eventual theory of gravity some 60 years later. Well, the third way is to model and discover new physics using powerful computers. This is a technique with significant origins during the Second World War in the making of the atomic bomb in Los Alamos, and as well as the development of solid-state electronics shortly after the war. And has come into prominence with the subsequent development of high-speed computers. Indeed, one of our little iPhones now has far more computing capacity than was available to the entire world just a few decades back. Well, Matthias is one of the great members of this third community of people who use computers. Born in Austria, he spent most of his professional career at the school, the ETH, the Federated Swiss
Federal Institute of Technology.
Swiss Federal Institute of Technology in Zurich, Switzerland, where incidentally Einstein studied from 1896 to 1900. And with the exception of a 3-year period where he was at the University of Tokyo, he spent almost his entire professional life there. Well, in the last few years, he moved on extended leave to Microsoft Research in Seattle to work full-time on the problem of developing quantum computers. While at Zurich, he became famous for his very ingenious use of computers to solve outstanding problems, such as discovering the properties of materials, predicting the properties of materials of ultra-cold atomic gases, and of quantum devices more generally. Matthias's talents in physics and computational physics have been well recognized by the award this past year, the prestigious Raman Prize of the American Physical Society, among many other honors. So let me now turn the floor over to Matthias, who will tell us about quantum computers and the future. So Matthias.
Okay, so first of all, the question I'm asked often is how come that a professor at the Deactivation Queue now works for a company? Why would I ever give up one of the best paying faculty positions, freedom in academia? And the reason was printed in the November 21st issue of the New York Times that Microsoft spends big to build a computer straight out of science fiction. They invest big now and they hired people, including me, as written here, to help them build a quantum computer. And that's exciting for me because, as you heard, I like working with computers, with fast ones, but I found that the biggest ones we had in the world were not fast enough to solve the problems that they really want to solve. And there's a company now that spends now lots of money to help me build something even better using quantum mechanics, using quantum physics. And so I used to simulate quantum physics, and now I help to build a machine that will even use quantum physics to compute. The other great thing is when you work at a company, you're no longer labeled, as we heard, by people who do experiments, people who do theory, people who simulate, people who are scientists, people who are engineers. I can do all of that now, and I can talk to VC people, to business people, to companies, and learn about finance as well. And that's been a great experience for me. But what is it that we actually want to build here, and why does a company invest lots of money to build a quantum computer? Let's go back in time to the first known computer. The first known computer was 100 BC, the Antikythera mechanism. A set of wheels that when you crank them could predict the positions of the planets and the moon. This was pretty complex in those days. When you cranked it, it showed you where the planets were. Then for a long time, there wasn't much that was better. The Babbage proposed the difference engine, which was a mechanical calculator that could compute. At that time, it was hard to build. Then the first electronic one was ENIAC in 1946. That was much more slower than my watch now is. The fastest one now is the Chinese one, the Tai-Hulite one, that can do nearly 10 to the 17 operations per second. So these are 100 quadrillion calculations per second. But this is not the end, because next we want to go to quantum computers that can solve problems that no computer that's classical, that's even as big as the entire visible universe, could ever solve. And those are the problems that I want to show you today. So computing has become cheap. Or when you look at what can you do with $1,000, when you started in the 1900s, you could build a machine. But the first ones, basically, you could do a few calculations per minute for $1,000. And right now, as I said, we are get machines that are much faster. So now we can do about 100 million operations per second for $1,000. It has changed by 17 orders of magnitude over a century. We went from things mechanical to relay, to vacuum tubes, transistors, and then to the integrated circuit. And then the feature sizes were shrinking, shrinking, shrinking. And so with Moore's law, we could pack more and more transistors onto a chip. And the machines just got faster and faster and faster at the same time. So currently, the speed of the fastest machine in the world doubles every year. And your phones as well, nearly. So, but this only works because we shrink things. And as we shrink things, things become smaller, and we reach the limit of atoms. So that shrinking will soon stop. And at the scale of atoms, the world turns quantum mechanical. And that stops our classical computers. But now there's the chance that we can change paradigm again. We can go from the transistor to a quantum device and say, let us embrace quantum mechanics, and let's use the new strange effects we have to compute better than we could do classically. Let's not see that as a problem, but let's see that as a challenge and a feature that we can do much more if we embrace quantum mechanics. And so the future of computing will be in quantum devices. You can already, since 5 years, buy quantum random number generators that give you true and perfect random numbers. You can buy quantum cryptography systems that let you encrypt what you send in an unbreakable fashion. You can buy quantum optimizers. The question mark is because they don't seem to work as well as one would have hoped. We can in the future build quantum computers. That's what we want to do now. For those, we know for sure from the start that when we build them, they can solve problems that no classical one can ever do. So let me start with random numbers. Who needs random numbers? Everyone needs it. Lotteries and casinos need random numbers. Now, these are classical balls, right? And you steer them up. And so if you knew where they started, where each ball was, then you could calculate the trajectory exactly, and then you can predict what numbers come out. And wouldn't that be great? Because this classical physics is all deterministic, right? If we know enough information, the rest is all given. There's no randomness in classical physics. When you have to the online casino, you have a program that runs, and the program outputs numbers that look random. If a hacker comes and knows your algorithm, the hacker can predict what comes out, and that's bad. So there you really want true random numbers that classical physics cannot give you. Simulations in science, simulations of the stock market and finance, it all needs random numbers. So let us think about how can we create random numbers using quantum physics for the first device. And that's a Swiss-made device that you can buy. It costs about $1,000. And the way it works, you have a light source, and the light source shines light onto a semi-transparent mirror. So now half the light goes through it, and half is reflected. Then the light hits two photodetectors. And what happens? The light is a wave, comes in here, and it hits the detectors. And what happens was found out first by Einstein in the paper for which he got his Nobel Prize. That's the discovery of the law of the photoelectric effect. What happens when the light wave hits some surface, that electrons fly out. But electrons are particles. They come from one location. And the light goes in as a wave. And he said the way to explain that is that actually the light is not just a wave, it is also a particle, a photon. It is quantized, that's the quantum aspect, into discrete particles that hit the material and kick out electrons. So that's what happens here. Now let us make the light very, very dim, so that it's not many photons that go there, but just a single photon at a time. So let's take here a single photon source, and the light comes, the photon comes, and the photon, this light particle, now hits the semi-transparent mirror. And what should it do? Let's ask Yogi Berra. When you come to a fork in the road, take it. That's exactly what the photon does. It just follows both paths. It goes to the left and to the right. It's now in both positions. And then it hits the detector. And the moment it hits the detector, an electron comes out and they see it. So the moment it hits the detector, it has to decide where it actually is. And then only one of those detectors can trigger, because there's only a single photon. It cannot hit here and there. So the moment it hits the detector and it's observed, it goes to either here or there. So it was in this quantum superposition, we call it, of both paths, until I start looking where it is. When I look where it is with the detector, then it randomly chooses one of the two locations, and it gives me a random answer, in this case, the left one is 0. And this is really due to quantum physics. Classically, you could not do that. And that we can now use to even compute. In classical computers, we have classical bits as the unit. They are zeros and ones, and we build up everything from zeros and ones. That's like a light switch that can be on or it can be off. It can be in the state 0 or in the state 1. But when you now go to quantum physics, then it can be in this superposition, like the photon was left and right at the same time. So this quantum bit can be on and off simultaneously. Now that's weird, isn't it? But you can to experiments, and that theory kind of describes what goes on. So we have to sometimes accept that this is how nature works. And so when things are very small and quantum mechanics is the right theory to describe it, then it can be both 0 and 1 on or off, pointing up or down. Or the simplest way is, you say, the classical one can be 0 or 1. And the quantum bit, we look at a sphere. And it's an arrow. If the arrow points up, then it's a 0. If it points down, then it's a 1. And if it points to the right, it is 0 plus 1. If it points to the left, it would be 0 minus 1, and so on. And it can point in any direction on the sphere. If it's up, it's just the 0, like classically, down, just the 1. The rest is all this weird quantum superposition. And this is really strange. And it's so strange that Schrödinger thought about it and realized, hey, if that is really how the world works, then you should see that. And so he came up with the Schrödinger's cat paradox, where he said there's a cat that is penned up in a steel chamber along with some hellish device. There's a Geiger counter and a tiny bit of radioactive substance. And it's so small that in 1 hour perhaps one atom decays or perhaps none. That means that after that time, after 1 hour, it will be in this quantum superposition of 0 or 1 atoms having decayed. But if you now think further about it, what happens when the atom decays? Then Schrödinger places a Geiger counter. The Geiger counter detects the decay. When it detects the decay, that releases a hammer that shatters a small flask of hydrocyanic acid. And then the cat dies. But now, this atom is in a state of decayed or not decayed. There are 0 or 1 atoms decayed. It's in this strange quantum superposition. And so what then happens is, we describe the state of this as a superposition of being decayed and not decayed. So then the hammer is in a quantum superposition of being up and down at the same time. So the flask is closed or broken at the same time. And we have a cat that is dead and alive. That's in a quantum superposition of being dead and alive. Have you seen a Schrödinger cat? When we want to build a quantum computer, we actually want to make such a Schrödinger cat, because those Schrödinger cats are really good at computing. So that's the challenge. We want to take it from the small thing to the macroscopic world. What happens? Why don't you see it? It's just like in the detector. The moment you look where it is, the moment I looked where the photon is, it randomly chose 0 or 1. So when I open the box and look inside, the system randomly decides between this being 0 and the cat is alive, or it being 1 and the cat is dead. So when I look at the quantum system, that quantum superposition collapses, we say it chooses one of the options that we used to. But it's weird. I still have problems grasping with it. How should I imagine it? But I'm used to it now that that's how the world works. But it gets even weirder. Namely, we can now take 2 qubits. Let me just find my qubits. Okay, let's assume these are 2 qubits. And now I put them into a quantum superposition of either both pointing up, so both being 0, or both pointing down, so both being 1. So the quantum superposition of 0, 0 or 1, 1. Now, what happens when I look at that? When I look at it, I get a random answer again, either 0 or 1. But because I initialized it in either being both 0 or both 1, if I look at it and I measure it, and one gives me 0, the other will also give me 0. If that one gives me 1, the other will also give me a 1. But which answer is random? So now, it's the same results no matter how far apart they are. I can take it now and prepare it in the state of 0, 0 plus 1, 1 in the superposition, and I give 1 to Gordon. And then I go back to Redmond and I look at it, and it's a 0. So now I know for sure what he will get. What do you have? I'm going to call you 0. It was random. It was not, yeah? It was not decided until then. We can try it again. I take the 2, and I take 1, and I give 1 to Jason Ho, and I ask him to fly to the moon with it. They still stay in this entangled state. They stay in 0, 0 plus 1, 1. They stay in that state when I look at it, and this time I get a 1. If Jason then goes to the moon and then looks at it, he also gets a 1. So it's the same random result no matter how far apart these qubits are. Now, of course, I can't send him to the moon, but what Chinese scientists have done, they sent photons through a satellite, sent it 1,200 kilometers away, and confirmed that this phenomenon takes place. So it has been used to space and back already. And this works. What's further is that when I make this state, and as I pass it along, for example, so I need my qubit back, and I take that now and I pass 1 to next week's speaker, Lincoln Carr. And if on the way there, somebody wants to eavesdrop on the line, they cannot do anything, because if that's the classical information, then the NSA might be able to intercept it. If this is a quantum bit that I'm sending Lincoln, then if somebody intercepts it, they will and look at it, they will destroy the state. So they cannot make a copy, because these quantum states cannot be cloned. So nobody can make a copy. That makes it really secure. If somebody looks at it, we can detect that. And they can't make a copy and then know that we both got a 1, for example. So we can use that for secure encryption. I send 1, or I now take 100 of them, I send them to Gordon, and we each have 100 random bits that we can use to encrypt any message we want to send without anybody being able to break it. We have secure encryption. But this whole thing of quantum mechanics and this entanglement and superposition is so weird that at the Solvay conference in 1927, many people, like we have here Einstein, we have Planck, we have Bohr, Heisenberg, Schrödinger, they all discussed what to make of this weirdness. And Einstein then wrote a paper in 1935 where he wrote up that this just cannot be the whole truth. It just cannot be that there's this spooky action at a distance. I send 1 to the moon and 1 here, and it is in the superposition until I look. And the moment I look, the qubit on the moon randomly becomes 0 or 1 without me doing anything to it. And Einstein just could never in his life come to grasp with that. And so he thought that there might be something different, that it might be that just I don't know whether it's 0 or 1, but it's already determined. And quantum mechanics is incomplete. It does not describe the whole truth. It just cannot be so strange. And it was undecided whether Einstein is right and there's something hidden here that I just don't know the state but it's determined, or whether it's really random only at the time when I measure. And what was then shown by John Bell that actually this question is not a philosophical question, it's a physical one, because one can do experiments that can test it. The latest one was done in Delft. Okay, they didn't send it to the moon, but just 1.3 kilometers apart. And what they can demonstrate is that the decision whether 0 or 1 is only taken when I measure, and this is really the way how physics works. It is in this state until I look at it, and that's just how it is. So we have to get used to this strange quantum mechanics. So with 1 qubit, we could get perfect random numbers. With 2 qubits, we could get encryption that's secure. Now imagine you have more. You have, let's say, 10 or so. Then they can be in a superposition of all possible values you can represent. So all the numbers 0, 1, 2, 3, 4, 5, 6, and so on up to 1,000. If you have 20 qubits, there are 2 times 2 times 2 times 2, there's a total of 1,000,000 total states. And you can now calculate with all of those numbers simultaneously. And that's the power of quantum computing. But first, let's see how do we actually build these qubits. It's not these dongles here. But qubits can be ions that one traps. I take an atom, I ionize it, I trap it somewhere, and then I encode the 0, 1 into the motional state. But there it's at rest or it moves. I want an ion and trap it so that it's very isolated from the rest, because I should not look at it. The moment I look at its state, boom, it's gone. It's 0 or 1. One can also take electron spins in silicon. That's the approach followed by Intel and many scientists there. I look whether the spin that is the magnetic moment of the electron points up or down, and that encodes the states. I can encode it in the electronic state of diamond defect. I can encode it in the way a supercurrent flows in a superconductor. That's the approach taken by IBM, Google, and the company Rigetti. Or at Microsoft, we want to build a topological quantum bit that I'll tell you about in a minute. The records so far are the ion traps in my hometown of Innsbruck in Austria, in the group of Rainer Blatt. He has 20 ions, so 20 qubits that work quite well. But the problem with all of those qubits is, okay, no, sorry. So, and if you want to use a quantum computer, 2 years ago at the big panel, I was told I should not talk about quantum computing because quantum computers don't exist and nobody knows how to program them. Now that was not the case then, because we had small things in the lab, but now every one of you can go online to the page by the IBM, get an account there, and run a program on a quantum computer with 16 quantum bits. They placed one in the cloud. So now nobody can tell us quantum computers don't exist because there's one in the cloud that you can actually program on your iPad. But the problem with all of those is when you look at the qubit, it is no longer in a quantum superposition. When I look at the cat, it is either dead or alive. When I look at the electron spin qubit, it's no longer in the superposition, there's now either 0 or 1, it's up or down. When I look at the superconductor, it does not flow clockwise and counterclockwise at the same time. When I check it, when I look at it, it decides randomly which way it flows. So any qubit, when I look at it, the quantum superposition is destroyed. So what we want to do at Microsoft, we want to build much better qubits that are based on Majorana particles. These are strange particles that nobody had seen in the nature until recently. They're named after Ettore Majorana. He was an Italian physicist who wrote down equations which found those new particles. And then, soon after that, he boarded a ship to Sicily and disappeared. That was in 1938. He disappeared. Nobody knows what happened. Some people think he might have jumped overboard. Some people think he might have been swept overboard. Some people think he might have stopped like King physics and became a monk. Nobody knows. But what we know is that the particle that he predicted was seen in superconducting nanowires a couple of years ago. There was a particle. There's not the particle like the electron or the proton or quark, but it's a particle that emerges as an excitation in a material. It's a so-called the quasi-particle. But there was this excitation here at the end of that wire that looked just like a Majorana particle. So Majorana finally reappeared. And we want to use these Majorana particles to build a quantum bit. And this is where the science fiction part of the New York Times might come from. Because we want to simply store the information of this quantum bit, the 0 or 1, in whether there's 0 or 1 electrons in a state. But of course, when I look at that, then I know there's one there or not. It's very easy. It does not stay in that superposition. And so what we instead do is we take this state, which is either 0 or 1 electron, and we split it apart into 2 of these Majorana particles. I have one here and one there. So these were either 0 or 1 electrons, and I'll take them apart. Okay, and one I move away. If I look at this here, I only know this is the Majorana particle. But it does not tell me whether together with the one that Gordon has, it forms an electron or it does not form one. So by separating the information, by taking the electron and splitting it into 2 parts, in a special material, I can make it robust, because I need to bring the 2 together again to find out whether the state is 0 or 1. As long as they're separate, it's protected. So we place them in nanowire about a few micrometer apart, a few millionth of a meter apart. And then we place them, and then if somebody looks on this side here, they can't know the state. You have to look at the whole device. And that takes effort. So this is encoded in a topological property of the state. What is that? If I take a strip of paper, then I can fold it together either as a simple band like I did here. Let's put it down. Just the normal band. Or I can take the strip of paper and I don't fold it together like the band, but I twist it once. Now I staple it together. When I look locally, they always look the same. But when I start painting them with color, then in this one here, I can paint the outside in red. I can paint the inside in green. This is two sides. And on this one here, because I've twisted it around, it only has one side. If I start here on the outside and I paint down and I go here, and I go here and I come up and I come back, because it's twisted, I come back on the inside, then I continue painting until I get back to the top. So this here, that's the Möbius strip, it's called, has only one side. The difference is not local, it's the same paper that is stapled together, but there's this global topological difference that I twisted it. And the only way I can find it out is I have to go along the whole way, the whole system all around it, then I know the difference. I can pass it along. Yeah. Yeah. So that's the same here. So, do you want to keep it or pass it on? Who wants to have it? Look at the two. So we take it, we put it apart, and if something comes in, if a photon comes in and wants to check is there an electron, it only sees the Majorana. It does not see the whole system. So you have to look at both ends at the same time to find out what the state is. That makes it much more robust. And that's what we want to build soon at Microsoft, and then use that to build a better quantum computer than based on the other qubits that exist so far. Now, what can we do with it? With a single qubit, there are two states, 0 or 1. With two qubits, there can be 4 states, 0, 0, 0, 1, 1, 0, or 1, 1. You go to 3 qubits, there are 8 states, 0, 0, 0, 0, 0, 1, and so on, up to 1, 1, 1. Each time I add a qubit, the number of states doubles. So with 4 qubits, I have 16 states. With 5 qubits, 32. When I get to 10 qubits, I get 1024 states. When I get to 20 qubits, like the ion traps in Innsbruck, that's 1 million states. So that I can describe on a classical computer with 1 million numbers. That I can still simulate easily on my phone. When I go to 30 qubits, I now have not 1 million states, I have now 1 billion states. That needs 1 billion numbers. For that I need something of a high-end laptop. When I go to 40 qubits, these can be in 1 trillion different states simultaneously. That needs the supercomputer. And the world record for simulating qubits are 45 qubits in the biggest simulation done so far, using the biggest supercomputer in Berkeley, and that was done by my students, Damian and Thomas. They didn't want me on the paper because they said they want to do that themselves. They want to have a student world record. Now, what if we go beyond 45? If you go to 49, 50, we may do that on the next supercomputer. But when we go to 250 qubits, the number of different states they can be in is more than the number of atoms in the visible universe. It's far more. It's actually even more than the number of quarks and electrons in the visible universe, and neutrinos. So you can never build a computer that can describe the state of 250 quantum bits. So once we reach about 250 qubits, we know that's a machine that's so amazing that I cannot describe it classically in the universe. And now the question is, what can I do with it? and now have all these these possibilities, and I can do a computation not just on one number like on a classical computer, but I can do that on all these possible numbers, 0, 1, 2, 3, and so on, all possible numbers at once, simultaneously. And that can, for some calculations, exponentially accelerate my calculations. One example is factoring numbers. You all know that 15 equals 3 times 5. When I ask you 21, then you tell me it's 3 times 7. But now I give you this number. Yeah. Here are the factors. How did I do that?
You started with those two numbers and multiplied.
Exactly. I started with two prime numbers, I multiply them. Because that way is easy.
I'm not sure.
The other way is hard. Yeah. So now this is hard unless you have a quantum computer. That's what Peter Shor showed. When you have a quantum computer, then this way is easy. So if you think that I did not multiply them, then you have to assume that I have a quantum computer, because quantum computers can do that. Why is that important? Because factoring numbers is hard. It is the basis of the public key encryption systems in the internet. The standard RSA encryption scheme gives people a public key with which they encrypt the text. But to decrypt it, you need a private key. And the public key is obtained from the product of two prime numbers. That's sufficient to encrypt the message. And the person receiving it needs to know the two factors to decrypt it. So if you want to send me an encrypted message, then I send you the product of my two prime numbers. You use that to encrypt the message, send it to me, and I can decrypt it because I have the two factors. But nobody else has it, because just knowing the product, it's very hard to get the factors. So it's safe until we get a quantum computer. Because when we have a quantum computer, then a number with 2048 digits cannot be cracked in less than 1 billion years on a classical computer. This cannot be factored. That would take 1 billion years. But if you have a quantum computer running at the gigahertz, it takes about 100 seconds. If it's slower, if it runs maybe only at a megahertz, it still takes only about a day. So with a quantum computer, suddenly you can factor these numbers. That shows you that some things that are essentially intractable classically become very easy once we have a quantum computer. Now, is that a good reason for building a quantum computer? Well, some people may want to have it, but as a business case for Microsoft, it's not a good deal. Because the moment you learn that I have a quantum computer, you will simply stop using RSA encryption. You will change to a new scheme that a quantum computer cannot crack. You will not do that when I have it. You'll start switching maybe 5 years before I have one. And then by the time I have my quantum computer, nobody uses RSA anymore. Except if somebody maybe has some archived messages they want to decrypt, but that's not our business. So what we've learned from there is that quantum computers can do some things that are classically essentially impossible, intractable, but it means also that you should soon change your encryption system if you want to keep a secret for the next 20 years. So anybody who wants to keep a secret for 50 years has already lost if they used RSA and somebody intercepted the message. If you want to keep a secret for the next 15 years, 20 years, think about the new encryption system. But what do we actually want to use it for? That's that's more valuable. We think if we have about 100 to 200 qubits, we can develop new catalysts for nitrogen fixation and make better fertilizer. With the same size, we can look at designing catalysts to capture carbon from the air and mitigate global warming. With about 100 to 2,000 of qubits, we can start solving problems in the material science and look whether we can find the better superconductor and maybe a room temperature one. So maybe we can use it to design a material that conducts electricity without resistance, without loss, without having to be cooled. We did not manage to get that yet so far. One reason is that we cannot simulate those materials. And with thousands, we hope it lets us improve machine learning, Skype translations, Bing search, and more things. Self-driving cars could be safer, and so on. So these are things that we think we can do. Let's look at one example in more detail. Feynman thought hard not only about physics, but also about how can you simulate physics with computers. And the problem is when you have these quantum systems, when you have 10 qubits, for example, or 10 quantum spins, there's 1,000 states. When you have 20, it's 1,000,000 states, and 30, it's 1,000,000,000, 40, it's 1,000,000,000,000, that a classical computer cannot cope with that. And so he proposed that you can build a computer based on quantum principles, the quantum computer, and use that to simulate nature. And then, as I said, you can look for new superconductors, new catalysts, new dyes that are non-toxic, new colors, new pigments. One example I want to look at is nitrogen fixation. That is the process of turning the nitrogen from the air into ammonia, which we use for fertilizer. And the way that's done now is you take nitrogen from the air, you take the hydrogen gas, you press it together, you add the catalyst, and it turns into ammonia, but it needs 2% of the world's energy, and to get the hydrogen, it uses 3% of the world's natural gas production just to make fertilizer. So it's quite expensive. At the same time, there are certain plants that in the root system have microbes, bacteria, that can do the same feat at room temperature. They take the nitrogen molecule, which are two atoms, and they break this apart without needing so much methane, without needing so much energy and temperature and pressure. And we want to, of course, understand how can they do it so easily. And this is the protein that can do it. It's a huge molecule. When the center, there's the active center that does the feat. So the red ones here are iron atoms. There's one molybdenum atom. And in the center, there's one gray atom, where until 5 years ago, one did not even know what atom that was. We now know that's a carbon atom. But a carbon atom surrounded by 8 heavy metals is so complex that this is intractable on a classical supercomputer. We have no way of simulating this molecule on the biggest classical supercomputers we have today. But if we get a quantum computer with only about 200 quantum bits, then we can simulate this. Then we can understand how it works how nature does it. That may give us ideas for how we can make the new catalysts that might give us cheaper fertilizer. We can do the same then with designing the catalysts for carbon capture and more. But we look beyond that because Microsoft is not the company in the fertilizer market. Although we might get into it if we get a new one. But we now look at, can we also use it to accelerate simulations of physics systems, of the financial markets? We look into, can we use that power for better predictions, better artificial intelligence, translations, searches, and so on. That would be a really big market. There can be even more. What you can do with quantum mechanics, just like I can encrypt something in an unbreakable way, I can also have a cloud service that is provably secure. I can do search and computing in a way that the owner of the computer on which I calculate it does not know what I calculate. I can use a quantum computer to do a search in the internet without Google or Microsoft knowing what the user searches for. Because Google doesn't like that so much because they want to sell you ads. But you may be willing to pay for a search that nobody can know what you searched for. You can even run calculations on some Russian quantum computer, and the Russians will not be able to find out what you calculated there. So this could be a big market. It doesn't have to be faster. It can just give you privacy. One can also think of quantum money. Money that cannot not be counterfeited. Money that is provably valid and true and secure. So there's much more we can do. And so what I wanted to show you today is that the quantum physics is not just something for physicists, but computing has entered the quantum age. We have true random numbers. Lotteries use them. Casinos use them. The reason why the casinos need them is they don't want the hacker to know the next number. The reason why lotteries want them is they don't want to be sued for having bad random numbers. But if they say we have quantum random numbers, then no lawyer will dare argue that it wasn't correct. We have secure communication that's unbreakable. And we're just about to have quantum computers that are more powerful than the fastest classical machine can ever be. Once we build them, they will be useful for code breaking, but also for privacy. They will help us design new catalysts, new materials. They may greatly improve artificial intelligence. So that's how much I can think of. But just like in the classical world, there will be great ideas by bright young people, quantum games or quantum Facebook or quantum networks. Like, I don't just want to have a friend, but maybe I want to be entangled with my friends. That could be a great thing. And then you need your quantum phone so that you can be entangled with your friend. I think that's the much bigger market than whatever we've found out so far. Because if you think back 50 years to ENIAC, one of the first electronic computers, who then would have imagined smartphones or Facebook? Right? So there's much more that we can do, and now is the time to dream about it and vision what will the quantum future be like. Think back 50 years. We now add the quantum aspect to it. It will be huge. And that's why Microsoft founded the Deactivation Queue with people in Redmond, Sydney, Delft, Copenhagen, and Santa Barbara, California. It started out in the year 2000 with Michael Friedman. He's the Fields medalist. He has proven the famous conjecture in topology. He's the member of the center here. And he said we should actually build a computer based on topology, on the strips that I handed around here. Then he founded the Deactivation Queue in 2006, and now grew with groups in Zurich, in Copenhagen, in Delft, Sydney, Maryland, Purdue, and Santa Barbara. We do theory, but we also build qubits, we measure them, and we want to, the next years, build a really great quantum computer. Thank you.
Thank you very much, Matthias, for lovely, lovely, interesting talk. We have time for some questions, for first hand, yes.
When you were speaking of entanglement,
Yeah.
science doesn't know what that is. When you guys hang around together, do you ever have ideas about what it could be?
I can only speak for myself. This is what we discussed with my when I was a student, and I learned about quantum mechanics, and we came to that. And we sat many evenings over beers or wine, and we discussed it, and we tried to grasp it. And at some point, we just accepted that that's how nature works. And yeah, we learned the rules, and we play by them, and yes. But I can't really envision it.
Nobody's studying how to try to figure it out.
People are studying about that, and whether it's really what we think it is, yeah, but it's really undecided until I have to look at it. And yeah, that's it's a big field in the quantum physics, thinking about that. Also, how does this cat suddenly become dead or alive when I look at it? That's also a big field of science still and research. How exactly does this happen?
Do you have an estimate on how much the first few quantum computers will cost to build?
An estimate. The first demonstration devices or the first real commercial quantum computers?
First real commercial.
The first real commercial ones, yes, I do have an estimate, and my estimate is at least as much as it costs to build a classical computer. And for the classical computer means you have to first build the fab line that produces those microchips. And this costs a few $1 billion. So that's roughly my price
Do you
tag.
think that technology is going to accelerate and get cheaper as much as computers that we have now have already?
I think we can use a lot of the classical technology to build also the quantum chips. But still, we have to build a new fab line specialized for that, and that's what it will cost. The quantum computer, in the end, if we then sell one, will be cheaper, just like your phones are cheaper because we make many. But the first ones, you have to build the whole fab already just for the first one. So that's roughly the the investment, and that's why it's big companies that invest not so much the venture capitalists. With the venture capital, you can look at parts of the stack, it may be the quantum bit or the software parts of the applications. But if you want to do the whole stack like we do, then you need a big sponsor. So that's also one reason why I switched to company, because we need much more money than we can get from grants in academia. Yeah. Sorry. Yeah.
How do you program and, more importantly, test a quantum computer? Because it's not deterministic. You don't get the same answer each time.
That's a very good question. The way we program it is the same way how we program a classical computer. I have one example here, just in case somebody asked. I can show you a slide. This is a program I ran last fall on the IBM machine. I write it just like a classical program, and just some instructions like here I say entangle the qubits. That's then the quantum operation. So it's just a entangle it or a measure. I do entangle and then I measure it, I look at it. Right? So I just write a program that looks like a classical program. Now testing is hard because it's not deterministic. Sometimes it is. So I can run programs that have a deterministic outcome, then it's easy. Like when I look for the factors of a number, then it might be just a single answer that comes out in the end. If not, then the way I test it is I have to just run it 1,000 times and see whether the probability of finding it agrees with what I expect.
So do you use a classical computer to check to see if you're
Yes.
or Monte Carlo?
I would use a classical computer to check small test cases. But we have the same problem in classical computing. I have a big program that I run on a 1 million CPU supercomputer. How do I ever know that it's correct? I test it first on a smaller machine, on a smaller problem. I run the smaller problem on the big machine. I run many test cases. I have certain limiting cases where I know the answer. So, and at some point, I feel confident that the program is probably quite correct. It will be worse here. Yeah.
How do the different technologies for qubits compare in terms of the number of operations you can do per second?
Yeah.
And how quickly you can interrogate the final answer?
So there's a difference in speed and there's a difference in quality. The spin qubits are very fast. The superconducting qubits also. The ion traps, because it's a big heavy ion and move around, are slower. But in the end, what is more important than how fast they are is how many operations can you do before some noise destroys your quantum superposition. And then most of these technologies have error rates right now of about 1 in 100. That lets you run maybe 100 operations. Now most programs are of course much longer. So you have to redundantly encode the information in not just one qubit but in many. And when you have these qubits, then you need thousands or tens of thousands of qubits to describe the quantum state in a stable way that lives for longer.
So when, oh, I'm sorry.
Yeah.
So in the plot where you showed, how long it would take to
Yeah.
create, an RSA key
Yeah.
with a classical computer or a quantum computer, you still had you had two different lines.
Yes.
For two different.
Yeah, for the speed, yeah.
Yeah. So how should I understand how close we are to, achieving the number of operations in a certain reasonable time frame?
We are far away. We can do about 100 operations. These need about a trillion operations. So we need much better qubits, or we need these codes on top of it, and then we need many more qubits. What we think is that the topological qubit that we want to build will have error rates that are much, much lower. Then they can run for much longer and will need far fewer. And we want to first make much better qubits before we scale up.
Matthias, I have two
Yeah.
questions. The first question is, I'm pretty sure that Microsoft is not the only company that is working on producing a quantum computer.
Yep. Yeah.
Yeah, and so what are the companies and which company has reached the most of all? Which company is closer than everybody else to produce this computer? Is it Microsoft or is it some
No.
other
Okay.
company?
So the IBM has put a 17 qubit machine in the cloud that you can use if you pay for it. Google has a 9 qubit machine that they published about. They want to have 49 qubits by the end of the year. Rigetti Computers wants to build one about the same size. They currently have about 8 qubits. In the labs in Innsbruck, they have about 20 qubits. The problem with those technologies is as you scale up, the qubits are not good enough, we think, to really scale it up to a real commercial machine. Google's goal is to build a machine that, although it can run only for maybe 100 or 1,000 operations, still can do something that is classically hard. But to get to real applications like factoring numbers or doing chemistry on it, you need a much bigger machine. And there we think is by first focusing on getting much better qubits, we will then soon pass them all. Because when you really want to scale big, when you want to run the marathon, you don't use your dress shoes and walk, but you rather go back, get your running shoes, and then pass the others.
This is pretty much the same question. Would you want to predict how many years it would take to pick some number like 40 qubits? I should add high-quality qubits. How many years from now might you guess one could have 40 high-quality qubits?
That's hard, but I think it's far shorter than most people think.
Why do you say that these, if you have a quantum computer,
Yeah.
you can't break the code? Why is it so private? What makes it?
What makes it private is that I take this entangled state of my 2 qubits, and it's in the state 0 and up at the same time. So yeah, in this state. And if now somebody looks at it in the meantime, they destroy the superposition, and that I can detect afterwards. I can detect if somebody looked at it in the meantime.
And you can't make a copy.
And so, so the eavesdropper can, so if the eavesdropper were able to make a copy, then the eavesdropper can just wait until we look at it, and then she looks at that as well and has the same number. But she cannot make a copy, because you cannot copy these quantum bits. But we can detect if somebody looked at it. So if somebody looked at it, then I say, okay, let's not use that. Let's try again because somebody interfered. But if we check and we find out nobody eavesdropped on the line, then we have these random numbers that only we two know and nobody else knows, and we can use that to encrypt the message.
So I have 2 questions.
Yep.
One's kind of a wild card. I'll ask the non-wild card first. So you were saying you'd need, with thousands of qubits,
Yes.
you could improve machine learning?
Yes.
So one thing I'm wondering about is, like, how did you arrive at the thousands of qubits? What kinds of improvements are you talking about? Have
Yeah.
you convinced yourself that with less you can't really do any like interesting improvements to machine learning? Because it seems like there's a lot of work being done there.
Yeah.
And
Okay,
second
yeah.
question, but
Good. Yeah.
should I ask it now or should I?
Ask both, and then I'll answer.
Okay.
Yeah.
And the second one is, didn't mention anything about quantum Darwinism. This work, I guess, from 2009 by Zurich at Los Alamos that seemed to kind of expand on our ideas of how you perform measurements in quantum mechanics. And I'm just wondering if that has any consequences for topological quantum computation or not. It doesn't seem to be out there in the literature, so yeah.
I can't really comment on the second one because I don't know enough about it.
Yeah, okay.
But the first one, I also don't know enough, so that's more the wildcard question, or it's our wildcard application. Okay. So we have a few quantum algorithms that can accelerate classical machine learning. But they give only a little bit of speed up. They might not be the big breakthrough. What our hope is that if I build a neural network from quantum bits and with a quantum circuit, then we know if I have about 250, what this does can never be predicted by any classical computer. So the hope is we can take a model like that, kind of a quantum model, and train it to potentially be much, much better than any classical model. This is a wild guess. But we know we have a machine that is exponentially more powerful than any classical one. So it should also better be able to learn things better than a classical one. Where does the size come from? When you look at big data problems, you have huge data sets. You want to learn like millions of points. And to represent that, you may need a few hundred qubits or more. We, of course, hope and we look for, can you do something with about 100? With 50, it's not enough because 50 I can simulate classically. It has to be quite a bit bigger than 50, but not too big. And that's where the guess of about 1,000 comes from, that we hope that with hundreds to thousands we can start.
Once again.